I think we've probably all sat through enough technical presentations this week. If your meetings have been anything like mine, there will have been discussions about research reports, and you will have looked at equations, some of which you may not have understood. I certainly know I didn't. So during this presentation, I'm only going to show one equation. It is not an equation used in design. However, it is an equation which should be seriously considered because it has a huge impact on any steel reinforced concrete structure. We have to ask why we are here. Why do we attend ACI conventions? We talk about concrete, rebar, additives, construction techniques. We talk about buildings, roads, bridges, other infrastructure. But what is it for? Ultimately, it's about people. We don't build infrastructure for the sake of the concrete. We build it to make people's lives better. So rather than delving into equations, I'm going to tell you about the best business trip I've ever done and the people I met. As a starting point, I flew from Gisborne in New Zealand to Brisbane on the east coast of Australia. The next stop on my island hopping adventure was Honiara, capital of the Solomon Islands. We didn't even get off the plane, but looking out of the window, could see members of the Australian Army protecting the airport. Then it was on to Nauru, where the runway was the length of the island. The local cop came out on his police issue mountain bike to put road cones across the road so the plane could get from the runway to the terminal. From there it was on to Tarawa, where the kids were playing football on the grass at the side of the runway. The dots of land were getting smaller. Finally, flew to Majuro, where the runway wasn't the length of the island, but it was slightly wider than the island. Majuro looks like a tropical paradise. It is. But it's a paradise with very limited resources. It's also a paradise where people have very little money. The reason I went there was because they were building a number of schools and college buildings throughout the island chain. The preferred choice of reinforcement was GFRP rebar. Here are some of the locations of the schools. These new schools were very important. The existing school buildings were repurposed coconut husk processing factories and buildings of that nature. So they were not purpose-built, and they were in a very, very poor state of repair. There are a number of difficulties in the construction. First, the islands are very remote. It is 4,000 kilometers from Australia and about 4,500 kilometers from Japan. So the import of materials is expensive. Buying large quantities of quality aggregate was going to be cost prohibitive. Furthermore, shipping the materials between the islands would typically be done in open-top barges. The journeys can be hundreds of kilometers. For example, Majuro to Rangalop is about 750 k's. Storage of aggregates is also less than ideal. They're typically piled on the wharf side without any protection. They look like piles of dirt, and that's the amount of respect they get. All of this means that quality aggregates are likely to become contaminated before use. The answer to all this, of course, is to source the aggregates locally. The aggregates used is crushed dead coral dredged from the ocean. The coral is contaminated with salt. It can be washed to reduce the salt content, but this requires a lot of fresh water, which is another scarce resource on the islands. They do have desalination plants on the main island, but capacity is limited, and desalinated water is very expensive. So it's easy to understand that with such pressure on resources, fresh water may not be available for the concrete. They do, however, have no shortage of seawater. The islands are protected by this big blue thing full of it. What we know for certain is that salt-contaminated aggregates were used. Whilst we know that, there is also a very high probability that seawater was used in some of the concrete, especially on the more remote islands within the chain. Here's the equation I promised. Iron plus oxygen becomes iron oxide. I don't know why we're all laughing. We've all seen it before. Everywhere you look. You go for a walk around the footpath around here, you can see the stuff. Chloride within the salty seawater acts as an electrolyte, allowing the iron to lose electrons more easily. This means the chloride ions effectively act as a catalyst, accelerating the oxidation or rusting process as we know it. There is another input to this equation, dollars. This input is required to offset the damage caused by the reaction. Repairs, maintenance, and shortened lifespan are extremely costly. To give an example of a shortened lifespan, this is a photo of the front of the hotel I stayed in. The building was around 10 years old, and as you can see, there was extremely severe spalling. The explanation I got from consultants was that the salt-laden coral aggregates were the most likely cause of the problem. The use of Mateenbar GFRP rebar in the new buildings meant the problem of rust was avoided. The use of salt-contaminated aggregates and likely use of salt water within the concrete no longer presented a problem. This helped save future infrastructure investment and repairs or replacement that these communities simply can't afford. Field jobs such as the building of schools and colleges really highlight the true reason we're here attending the ACI convention and this next workshop, getting together, improving and expanding the knowledge of concrete construction to make people's lives better. The design engineer and the construction companies involved all had the foresight to build infrastructure that would last. These days, sustainability cannot be ignored. Forward-looking government departments have recognised the need for sustainable strategies. Resource scarcity must also be recognised. Resilient infrastructure is critical, but over time, engineers will be forced to use contaminated aggregates and even brackish or seawater in their concrete, whilst still trying to guarantee longer lifespans for the infrastructure created. The use of Mateenbar GFRP helps engineers to achieve these two previously conflicting goals. I'm not a fan of reading out things from a slide, which the audience can read for themselves, but in this case, I think the motivation statement of the ACI 243 committee is worth reading. Conserving fresh water and natural aggregates is a global goal in concrete technology. ACI 243 will facilitate the development of knowledge and documentation necessary to attain this goal, as well as motivate improvements to the service life and resilience of concrete in saltwater environments. This will be critically important and will be of huge benefit to many of those communities who don't have access to large quantities of fresh water and high-quality clean aggregates. Environmental changes in the world will make this even more important. We supplied Mateenbar to about 13 school buildings. Those buildings are now 20 years old and still in great condition. To finish on a high note, this is without doubt the best job I've ever been involved with. These are people who have very little and can't afford to rebuild the schools. They are the friendliest people you will ever meet. You walk down the road, these kids, they will put their hand up and give you a high five as they walk past you. These people have almost nothing, but always have smiles on their faces. I like to think we've helped contribute in a small way towards building them a legacy. Our company motto or tagline is creating lasting material change. We're changing traditional materials to options which last longer, but more importantly, we are making a lasting material change to the lives of people, including the Marshallese that I was fortunate enough to meet on this incredible trip. I'm guessing this wasn't the type of presentation you were expecting this morning, but I hope it's been at least a little thought-provoking and reminders of the importance of our work. Thank you.